Hello. We are going to continue about statistics in this video, and what we have done up to this point is basically MLEs, a little bit of MLEs, and a little bit of estimation and stuffs like that. So let me recall what we have done until now. It was MLE, it was point estimation, so these are the things we have done, and we would like to do some more. Now, what happens is once we try to get hang of this test statistics and this stuffs like this, what we actually want is to understand the ideas behind these topics, right? So in statistics, what happens is when you have a data set and you're trying to manipulate with it, you're trying to get some information about how the data set acts, how it works, or you maybe graph it. So let us say you have a data set x1 x2. Let me write it down. We have a data set x1 up to xn. Now in this data set, what we can do is we can see that x1 x2 up to xn is a data set, and the properties described by this data set could be as follows. The mean is written like this with the x bar. It is called the sample mean because we believe that this data set x1 up to xn, if it is not the population, then it was taken from the population by some sampling method. Now there are a lot of sampling methods in existence: uniform sampling, random sampling, and then there is collective sampling and lots of others of them. Okay, cluster sampling. So a lot of types of sampling are there, and they were taken by any one of those methods or a completely new one maybe. But anyway, they are members of the population and they represent a sample of the population, right? Our target is to understand the features of the population given this sample. So firstly, the sample mean is this. Okay, this is the sample mean, and we also know the variance is let me first I have already defined you moments, but I'll just write it down again. The average, which is given like this average e of x, or the expectation of the data set, if the data set is continuous, maybe discrete here in this case, then it is basically equals to the sample mean, right? And this sample mean is the best estimator for the population mean. So if the population mean is mu, this means that expected value of x bar is simply equals to mu. Okay, now there are a few other things we should note, that we have studied this kind of things, and what we would like to understand is what is a z score now. So we would like to understand z score. So how is a z score related and what is a z score? So z score comes from the z distribution. It is a standard normal distribution. So let me give you an example. Given x is a random variable following normal distribution with parameters mu and sigma square. Okay, find the z score for. Okay, so we want to find the z score for some value, and we are not entirely sure how to do that. But if you are asked to find the z score for some x equals to k, then the z score for x equals to k would be k minus mu by sigma. This is the z score. So what it means is that the z score basically follows the normal distribution. Now, how to find probabilities of certain things? So suppose we have to find probability of x less than equals to alpha. Okay, so if this is the case, then what we do is we see that we subtract by the mean on both sides first, then we divide by the standard deviation. Now since x is if x is basically directly normal variable, it's fine. But if x is just a representative of a sample which has n entries in total, then what we do is this: we multiply it by root n on both sides, and same here. Now this x minus mu by sigma multiplied by root n. Now let t equals to root n by sigma into x minus mu. We can show that t is standard normal. That is, t goes from normal of 0, 1. So when this happens, what we see that therefore probability of x less than equals to alpha, this value would just be probability of t less than equals to root n times alpha minus mu by sigma, right? And for the standard normal variable, what the answer would just be minus infinity to root n of alpha minus mu by sigma 1 by root over 2 pi e to the power minus x square dx, or it can also be written as phi of root n into alpha minus mu by sigma, where this phi represents the standard normal CDF, where phi is this, right? Now the integration parts and all these things, the prerequisite for integrals would be embedded from my previous videos as well. You will get that. But the question here remains that when phi and when we have the standard normal variable, we can easily find out, and this is essentially what we call the z score. The values of the standard normal variable for different probabilities have already been listed out quite often, and what we can do is we can understand if this function really is required in order to understand all the different properties of any probability we ever get. And when the values are like large enough, or when the sample size is large enough, obviously, then every variable can be approximated into the standard normal variable distribution, and this is basically where the central limit theorem comes into play. So what is the CLT? Given a random sample xn, where x bar is x1 plus x2 plus xn by n, and variance of xi is sigma square less than infinity. So when you have the mean and the variance of each of them, they come from the same distribution, which are IID. Of course, I want to write IID here, and this sample mean is mu. So basically, what I want to do is E of xi is mu. Okay. So when this happens, we can write the CLT states that this, or in other words, or what you can do is you can write like this: probability of x bar less than some t can be written as probability of z, where z is a standard normal variable, less than t minus mu by sigma square by actually sigma by root n, not sigma square. So let me correct this part. Sigma by root n. Right, and this only happens when you have limit n tends to infinity. So it basically becomes phi z of t minus mu by sigma by root n. So this is how the CLT works. So it can be for any distribution. It may be for a binomial distribution. It may be for a Poisson distribution. It wouldn't matter really, but it can be for any distribution. And the prerequisite for this variance and exponential stuff would be given at the end of the video as well. So you can check that out as well. So this is the CLT, and we will talk more about it and solve maybe after that, or maybe some problems at the end. But this is it for this one. So enjoy the prerequisite. So in statistics, we deal about something called data. When I say data, what I mean is we have clusters of points which represents some identity or some information about a certain quantity, and we would like to investigate about those data points or those cluster of points, and we would like to find certain information about it. For example, what we can do is we can measure heights of certain people. So let's say we have 10 people, and what we do is we measure heights for each of them. What we can do is we can name the heights measured as x1, x2 and all the way up to x10. Let this be the data points. Okay, so what are these? These are the data for our sample experiment or whatever we're going to do. Now using this data, what we can do is entirely a different subject, because there are a lot of things we can try on this data, but for the basics, for the sake of basic statistics, what we can do is we can find the mean, the mode, the median, we can find the skewness, the kurtosis. Also we can see if they fit into any probability distribution, and moreover what we can do is we can find probabilities of certain heights being improbable or certain heights being like very likely, right? and maybe there are more than 10 people, maybe there are like 1000 people, and we did a random sampling of those 1000 people, and we selected 10 people at random, and then we selected the heights, and from this heights what we need to do is we need to give a general idea about what would happen to the heights of the other people, or you can say the height of the population, which is of the 1000 people. Can we get an idea about the height of the population from the height from the data points secured in this sample? That is the ultimate question. That is, let us say we were trying to investigate some statistics about the whole country, and you know there are a lot of people in the country, right? So let's say there are 100 crore people right now, for example, and what we want to do, we cannot sample 100 crore people, that would take a lot of time, and that is why we are being realistic here. We are not really being mathematical, because in mathematics we can even sample 10 to the power 100 people, right, with in a finite number of years, but that doesn't make sense. So let us say we can sample 1 lakh people or 100,000 people, and we would like to get an idea about the whole population from the sample of this 100 lakh people, 100,000 people. And what we would like to do is we would like to select them randomly and uniformly from the population, so that no selection is biased, every selection is uniform, and every selection is equally likely. When we do that, the question is, can we get the idea about the whole population? Ideas like what is the average height of the population, ideas like what is the height that goes on the furthest, above which range do we have a 20% chance of getting a certain height, and stuff like that, you know. So we shall begin with something called mean. So what is the mean? Let me write it down. Right. Similarly, the median. So if this is the mean, the median is given by and after we are done sorting the data in ascending order, what we need to see is the middle points. Now since there are an even number of them, there are two middle points, that is x5 and x6, and they contribute to the median m, which is given by the average of this two. Okay, and if it were not the if it not were even, let us say we had 5 quantities, then there is only one middle number, that is the third one, so we only take that one, right? So it makes sense, because what we understand from this kind of criteria is that we need to be clinical about our data set, and there are a lot of things we can do with the data, and it's usually a good idea to sort them into ascending order before doing any calculations, because it helps us figure out how the data is increasing. We can also graph the data. So this mean, this median, whatever we're talking about, these are called statistics. So statistics are basically a function of the data points. So An example of a statistics would be so covariance of x comma y would be e of xy minus e of x into e of y, right? Where e of y is defined as integral over all r y into f of y dy, and e of xy on the other hand is basically a double integral where fxy x comma y is the joint distribution of x and y. So this provides the way to make sure that we have our expectations correct, and obviously integration is very much required in each of probability and statistics courses, because integration and derivative, they form the base of calculus, and in each step we shall find ourselves to be doing some kind of integration or differentiation, right? So that is one way. Now let us see what we can do with some of the things we have here. Let us begin with a topic here. So what is point estimation again? So we have talked about it before in probability, but let us talk about it in detail here. What is point estimation? Suppose we have B, a point estimator, for a parameter theta. Now what we do know is bias of a estimator is as follows. So bias of an estimator is given by expected value of the estimator minus the estimator. You see, so that is how bias is defined, and we call it unbiased if bias is 0. So we call so if this happens, we call our estimator unbiased, right? Now we can take an example to see that why this is the case and how we can prove such questions. So let us take a small example. So that is the question in we need to show, not of itself, obviously it's unbiased estimator of theta equals to exi. The parameter is theta, which is equals to e of xi for every I, right? So how do we show that? We see that e of this phi cap is basically e so now we use the properties of expectation as follows. Therefore, we see that e of phi cap is basically equals to theta, which means it's a phi cap is an unbiased estimator of theta, and that is why it is basically unbiased, and the problem is solved. Now, this is how we solve this problems, and showing that something is an unbiased estimator specifically involves finding the expectation of the point estimator, and this expectation may well involved some kind of integration or summation, which we have discussed before, I think, and those are required. Now, after this, what we will learn is the mean squared error. So this is the mean squared error, because phi cap minus theta is the error that we make when we are going to estimate theta based on phi cap, because see, phi cap is an estimator of theta, right? But since we say estimator, we are not really guaranteed that phi cap would always equal to theta, so it estimates theta, so there can be some error, and that error is given by phi cap minus theta. And mean squared error is basically we square the error first, which is phi cap minus theta squared, and then we take the mean of it. And in statistics and probability, when we say mean, we always mean the expected value, because the parameters and everything else, they can be a continuous random variable or a discrete random variable kind of thing, and we need to do integration or summation over that, right? So that is one way. Also, what we can find out from this is So the MSE is basically the equal to variance of the estimator plus bias of the estimator squared. This is another way to find out that. Now, here comes an important property of showing something is a consistent estimator. So our topic is how to show how to show if some estimator is consistent, right? To do that, what we can do is we say minus theta is greater than equal to epsilon and this is equals to 0, of course, for all epsilon greater than 0. So this is basically the definition for the epsilon delta case and stuff like that, and we can make sure that this works. So let us do one example for that. Suppose x1 x2 all the way up to xn be a random sample with mean e of xi equals to theta and variance of xi equals to sigma square. Okay, we need to show that is an consistent estimator of theta. And obviously we first do the integral definitions of this. We want to say that this is, since let fxx be the common PDF, then exi is simply fx dx, while variance of xi is x minus exi squared fxx dx. Okay, and we want to show that theta n is a consistent estimator, where theta n is basically equals to the sample mean. So given and we would like to show that this is the consistent estimator of exi, and let exi be equals to theta, which is also given. So therefore we need to show the following. So then probability that theta n cap minus theta absolute value is greater than equal to epsilon is equal to, so what we do see here is that they have a common PDF and they would like to, they can be treated as equals, right? Now this means that what we can do is we can use the Chebyshev's inequality here, because we see that E of theta n cap is E of 1 by n summation of I equals to 1 to n xi, which is 1 by n and this becomes theta, right? Therefore using Chebyshev's inequality we have less than equals to variance of theta n by epsilon square, and now variance of theta n is basically variance of x bar by epsilon square. Now what is variance of x bar? Variance of x bar is simply equal to and this would be 1 by n square variance of summation from I equals to 1 to n xi, and this would be n into sigma square, so it becomes sigma square by n, right? Therefore probability that theta n cap minus theta is greater than equal to epsilon is less than equals to sigma square by n epsilon squared. Therefore limit n tends to infinity, probability that theta n cap minus theta is greater than equal to epsilon is less than equals to 0, and this means that obviously since probability can always be is always greater than equal to 0 as well, therefore limit zero. So theta n is an estimator of theta, and this is proved. Limit n tends to infinity, probability of theta n cap minus theta. Theta is the parameter which theta n cap is estimating, of course, greater than equal to epsilon is equals to 0. So we say that theta n is a consistent estimator if the following property is satisfied, right? Now obviously we also defined that MSE of theta was simply equals to expectation of theta n minus theta, actually theta n's MSE squared, right? Then we see that if limit n tends to infinity MSE of theta n equals to 0, then theta n is consistent. This is another property. We can prove it as follows. We see that and this thing here, right here, we can obviously understand that this is less than or equals to the variance and bias, right? So what we can do is as follows. This is by Chebyshev's inequality, but the above thing is just MSE of theta n, right? And this would be 0 because we know that limit of MSE of theta n is also 0. And if that happens, theta n is again a consistent estimator. Now that being said, what we would like to do now is this maximum likelihood estimation. Now, what is a maximum likelihood estimation? Well, obviously, when we have an MLE, we also call it MLE. When we have an MLE in form, what we do is usually estimator for a random sample is given by, so this random sample is given by so this is our maximum likelihood estimator defined, and we do this like this. So we take the product of the PDFs basically, and the PDF is dependent on some parameter theta which we are estimating. So that's how we do it. So we are trying to estimate the probability or the value of theta for which the likelihood is maximum. Okay, so that is what we are going to expect here. Now how do we evaluate this sum? Well, obviously now we turn back to our calculus days and we remember that we can take logarithm on both sides. So and taking the logarithm of this would give us right? And what we can do is we can define this one as, let's say, log of capital L, and log of capital L is equal to this, and we need to maximize log of capital L. So differentiating both sides, we have, so firstly the question asks us how do we differentiate it both sides, right? So, well, it's obviously L prime by L, and we are differentiating it with respect to theta, of course. Okay, so since we are maximizing theta, we are differentiating it with respect to theta, and differentiating, you get something like this. Comma theta. Therefore, L prime is equals to xi theta divided by fxi xi theta, and this is equal to 0. And when this is equals to 0, we can find out certain values of it. So whatever theta we get is called theta mle, which maximizes the likelihood. And we sure would see some example here, and that example would be this. The example is crucial to understanding what we are doing, because otherwise we would never know how to apply it. So the example is, suppose I'll just write down the question first. So we have observed the random sample x1 x2 all the way up to xn, and suppose we have that this xi's belongs to normal distribution of theta 1 comma theta 2, right? So what we need to do here is we need to find out the estimators for theta 1 and theta 2, and we also need to find out the maximum likelihood examples. Okay, so what we need to do here is obviously the PDF for all the xi's given the two estimators theta 1 and theta 2, or the two parameters, is given by 1 by root over 2 pi theta 2 e to the power minus xi minus theta 1 squared by 2 theta 2. Now let us find out the actual value, and let us see how do we do it. So the likelihood function, to find the likelihood function, we see this is the expression, right? And with this expression we see that we can write this as product of I equals to 1 to n, and this L is basically the likelihood function which we will be defining now, and well in the upcoming examples as well we are going to use the same likelihood function for x1 up to xn, and it doesn't matter how many parameters are there, we can estimate them all. So this gives us this would be, since the 1 by root over 2 pi theta 2 is a constant independent of I, we see this is equals to 2 pi theta 2 to the power minus n by 2, and the exponentials are all, the product of two exponentials simply adds up the argument, so it's basically exponential of this, right? Now therefore taking the logarithm on both sides, ln of L should be equals to minus n by 2 ln of 2 pi theta 2, not a plus actually because we have exponential of minus, so exponential and logarithm are inverse functions, so log of exponential is just whatever is the argument, so minus right. Now to find out the expressions and the maximum likelihood expressions for theta 1 and theta 2, we need to do them one by one. So let us start with theta 1. Starting with theta 1 we have, and obviously all the derivative formulas and stuff and integration would be required here, so that would be embedded with this video for your forsaken needs. This would be 0, while this would be 2 times therefore this gives us L prime by L equals to minus 2 I equals to 1 to n xi minus theta 1 by 2 theta 2, right? And setting L prime equals to 0, we have we see that summation of I equals to 1 to n xi minus theta 1 is equals to 0. This means that n theta 1 is equals to I equals to 1 to n xi, or theta 1 is just 1 by n I equals to 1 to n xi. Therefore, the MLE has been found, and it is 1 by n summation of I equals to 1 to n xi, which is just the sample mean. Now let us do the same method for part 2. Now the first term was minus n by 2 log of 2 pi theta 2. This one would be useful here, and thus we have minus n by 2. Differentiation of log of 2 pi theta 2 is basically 2 pi theta 2 2 pi, and this one, the only term here is 1 minus 1 by 2 theta 2, which would be basically minus 1 by theta's differentiation is 1 by 2 theta square. So this term 1 by 2 theta 2, so this minus 1 by theta 2 will only be differentiated, right? And this is theta 2 to the power minus 1, and when differentiated this will become minus 1 to the power theta 2, so basically it's 1 by theta squared. So this would be plus 1 by 2 theta 2 squared I equals to 1 to n xi minus theta 1 whole squared, because this term acts as a constant, right? And therefore L prime by L is minus n by 2 theta 2 plus 1 by 2 theta 2 squared I equals to 1 to n xi minus theta 1 squared. Setting L prime equals to 0, we have therefore and this is just sigma square, right? Therefore we see that theta 1 MLE is just x bar, while theta 2's MLE is sigma squared, and this is how the likelihood is calculated. So I'm just basically writing down what we have done in the last ones, so that we understand how to basically come up with the next set of rules and functions for this. So this was the condition for differentiation at the point A. So what we did find was, if we are given a function f from the Euclidean space r to the power n to the Euclidean space r to the power m, we have that if it is differentiable at some a belongs to r to the power n, then there exists a linear transformation lambda which is from r to the power n to r to the power m like this, and the following limit satisfies, that is limit h tends to 0, norm of f of a plus h minus f of a minus lambda of h divided by norm of h goes to 0. So this was the whole definition, and we also found out that lambda is unique, right? So this was our findings for the last session. Now in this session we would like to go ahead and prove some more things. So but for that we should take a look at how do actually higher dimensional derivatives work. So if we were to do the following, I'll just write down the question here. Now we are required to find out the derivative at a, that is we have to find out this quantity, that is the derivative of f at a. Now notice that whenever you have like a function from higher dimensions, the derivative is not really a single number as in the case of one variable calculus, right? So it's a derivative from r squared to r, and of course this would mean that it's from r to the power 2 to r to the power 1. So the derivative would be a matrix of dimensions 1 cross 2. So whenever you have a function from r to the power n to r to the power m and you find out its derivative, it's always, the derivative is like always, since it's just a linear transformation, the matrix of the linear transformation would be a m cross n matrix. So here it's 1 cross 2 matrix. Now this means just 1 rows and 2 columns. So anyways, we can get to the part easily. We know that sin x's derivative is just cos x, right? Then now if we were to just guess that the derivative of fxy is just cos of x comma 0, we could have done that, and what we can achieve from that is as follows. We can guess the derivative already. That's one way to solve a problem like this. We can already guess the derivative, and then we can use on that to find out our findings. So we can write like this for two-dimensional functions. So it's just like iterated limits, but this works. Now our linear transformation lambda, we want that to be cosine of a into x, because at a it's basically cosine of a. So we have limit h comma k going to 0. Now after this definition, since we know that so this helps us say that, and since also the numerator consists of only real numbers, we can say that the norm is basically the absolute value first of all, and when we have this norm thing here, we can understand that since hk is greater than equal to this should be less than equals to limit h tends to 0 sine of a plus h minus sine of h minus cosine of a into h by mod h. But this is already 0. This is 0 because we know that derivative of sine x at a is basically cosine a, right? So we already know this part. And since we know this part, we can conclude this, since this is less than equals to 0, from like our previous experience, we can say that this modulus is also greater than equal to 0, and thus therefore limit is 0. Therefore it is easy to say that d of f, what we want to do is ab, so let us do it from ab. So derivative of f at a comma b is cosine of a. That is our answer. Okay, so this completes our problem. Now it is of paramount importance here that we understand that the rules of one variable calculus sometimes also translate back to this multivariable calculus. That is, we can prove the following. such that so we are required to prove that if f is a function and f is from r to the power n to r to the power m, and it is differentiable at a belongs to r to the power n, then we are required to prove that it is also continuous at r to the power at a, which is from r to the power n. So this is a direct analog of the property in single variable calculus, which says that if a function f is differentiable at a point a, then it is also continuous at the point a, but it is not necessarily true the other way around, right? Because differentiability is a sufficient condition for continuity, while continuity is just a necessary condition for differentiability. So let us think logically and understand what we can deduce from this. So obviously, let me just write down the given parts first, then we can try and figure out, by using all the details we have learned, to see if we can correlate one another. So, well, differentiability at a point in higher dimension means that there exists a linear transformation lambda such that df of a becomes lambda, right? Now, this means that this lambda also satisfies the property that the derivative satisfies. So we can write down now the limit that norm of f of a plus h minus f of a minus lambda of h divided by the norm of h equals 0 as h tends to 0. This is the limit that it satisfies. So it means that the term in the numerator, which is f of a plus h minus f of a minus lambda h, this term is a good approximation, right, to 0 right now. So there is an error term r of h, if we allow it to happen, that when added to the numerator would give us something like this. So firstly, we understand that f of a plus h is quite well approximated by f of a plus lambda h. But if we want to approximate it further, what we can do is we can write, since there exists an error term which is epsilon of h such that f of a plus h minus f of a is equals to lambda of h plus epsilon of h, where limit h tends to 0, epsilon of h is norm divided by this h is norm goes to 0. And this is true, and you can find out that this is pretty much reasonable, and this also forces the above limit. So this error term must go to 0, right? Now from this limit it is pretty much clear that since now this is a conclusion that we can make, obviously, and this conclusion gives us a way to frame that the error term goes to 0, the norm of the error term goes to 0, right? Now this says, and also if we can prove that the limit for the linear transformation goes to 0 as h tends to 0, we are done, and you will see why. Because now also if h equals to I equals to 1 to n hi ei. Here ei's are the standard basis of r to the power n, that is here firstly hi belongs to r and ei's belong to r to the power n, where ei is just 0, 0, 1. This is at the ith place, 0 and 0. So this is the standard basis for r to the power n, as we all know from linear algebra. And let us say the vector h is consisting of has this representation, then so that is how lambda of h will be written as. Now using the properties of linear transformation, we can write this as well, so lambda of this basis, right? Now what we can see is that if h tends to 0, then for all I belongs to 1 comma n, hi tends to 0, right? Because when the vector h goes to 0, all of its components go to 0, and therefore limit h tends to 0, lambda of h is simply limit h tends to 0 and this can be written as and this term goes to 0, right? So we have a 0 in total. So this proves that limit h tends to 0, lambda of h is also 0. And together we have proved something very important. Now what we can do is recall that now taking the limit we have now this proves that since we have this part obviously, and both of these limits go to 0, so this is 0, and from this we can conclude that therefore limit h tends to 0 f of a plus h is equals to f of a. This means that f is continuous at a. So differentiability implies continuity. So this was not really the hardest problem, because obviously you understand that this problem here uses the basic definitions and just logical thinking to come to the conclusion that differentiability of a function shall always imply continuity. Okay, and that's not really a hard nut to crack. Now some of these things would require proof and some of them would not, because the first one seems like a pretty easy thing to do, because we can prove the first one as follows. Since f of x equals to y for all x belongs to r to the power n, and we need to prove the derivative is 0, so let us prove it at an arbitrary point h. Limit h tends to 0 f of a plus h minus f of a minus 0 divided by mod h. So this limit should be 0, and we see that limit h tends to 0. Now f of a plus h is y, so is f of a, because it's a constant function, right? And of course with the norms. So this is basically 0 because the numerator has norm 0. So therefore df of a is basically 0, right? Number 2, so since f is the linear transformation here and we want to prove that the derivative is itself, we can say the following limit f of a plus h minus f of a, and this answer should be f of a into h, right? So like this should be the answer that we are looking for, and it shouldn't be f of a into h, it's basically f of h basically. So we can cut this part down, because when you have the function f and the derivative d of f h should be given by f of h. So because that is what we are trying to prove here. But since f is the linear transformation, we see that if you were not clear about this, so there exists a linear transformation lambda h, but we want to prove that the linear transformation is basically the linear transformation that we had before. So starting with the linear transformation, that linear transformation is always differentiable. We have proved that the linear transformation is always differentiable in one of the previous videos. So in this case the answer should be f of h, the derivative should be f of h itself, and we are trying to prove that this limit is 0 so as to establish that fact that the derivative is itself. So we see that since f is a linear transformation, it follows the property of a linear operator. So f of a plus h is basically f of a plus f of h, and we already had minus f of a minus f of h equals to 0 because the numerator is 0. Now, well, this can again be done because we see that this kind of problems can be easily done using all the proper things. Now the proof of number 3 should be something like this. Now we know that we can assume that each fi is differentiable at I. So if each fi at A, and we are claiming that the derivative is this, now what we want to prove is that limit is true. Now we can see that f of a plus h minus f of a minus lambda h is basically equal to, now this whole thing can be found out because it's basically a vector now and f has component functions. So we can see that the first component is this minus this minus this, second one is this, and similarly the last one should be this, right? Now therefore limit h tends to 0, f of a plus h minus f of a minus lambda h divided by norm of h, this limit then should be equal to norm of, we know this vector is basically represented as this, and when we take the norm of that, it's basically a summation but in square root form, but we can, since we have already proved that that is less than equals to the mod of that, so what we can find is this is less than equals to summation I equals to 1 to m fi of a plus h minus fi of a minus dfi of a mod of this divided by mod of h. And we do understand that this, all of this limits goes to 0. This is because since fi's are differentiable at A, so because this is true, we know that limit h tends to 0 fi of a plus h minus fi of a minus dfi of a, which is basically the derivative for fi, divided by mod of h equals to 0 for all I belongs to 1 to m. And that is why this is also true, and this proves that the limit is 0, right? So this is another way of doing it. Now if we are given, let's suppose we can turn our attention to a more simplified problem I hope we can do that. So let's say if and s of x comma y is basically x comma y, then we need to prove that ds of a comma b is basically s itself. It's basically s itself. Now how do we do that? Well, we see that we can directly find out the limit here. Limit h tends to 0, and let us see the norm, because it will be normally a modulus, because you understand that firstly, because the output is always a real number, we can have a real number here. So what we have here is as follows. S of a plus h minus comma b plus k minus s of a comma b, and we are calling the linear operator lambda of h comma k, which is basically s itself. Now we want this limit to be 0, or we want to prove that this limit is 0. So let us see how we can do that. Well, s of a plus h comma b plus k is basically equal to, since s of x plus y is defined like that, so a plus b plus h plus k, this is like minus a minus b, and lambda of h comma k, since we want the derivative is itself, it's basically minus h minus k divided by root over of h squared plus k squared. But this is equal to 0 since the numerator is 0, and therefore it is proved that ds of a comma b is simply s. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes, where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes, we have already explained all the examples, all the problems in theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also, you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.